Oh, I can give you another one. Thank you.
Good morning, everyone. Welcome to the Pactrans Transportation Seminar. It's our great pleasure to have Professor Framewo come here to talk about his research. Maybe a lot of you know him already. Henry is a professor at the Civil and Environmental Engineering Department at the University of Michigan. He's also a research professor at Michigan Transportation Research Institute. Similar to me, he's also directing US DOT funded University Transportation Center. His center is Region 5 Transportation Center, titled for Center for Connected and Automated Transportation. This is what you know about the professor side. Actually, Henry has been an entrepreneur. He took a leave from University of Michigan and served as the vice president and the chief scientist for the Urban Smart Transportation Unit at BD Chuxing Corporation, one of the biggest mobility service provider in the world. While he was at BD Chuxing, he actually built the Smart Transportation Urban Unit. And he now returned fully to University of Michigan. Henry's main research focus on transportation network modeling, monitoring, and also mobility and safety applications using connected and autonomous vehicles. So let's welcome Professor Liu for the seminar talk.
Yeah, thank you so much. Can you tune down a little bit? I tend to be loud, so yeah. And this is a seminar, long overdue. Jeff invited me, and about 2 years ago. So it's a pleasure to be here and finally have a chance to visit University of Washington. It's so far has been a great day, great conversation with faculty and students. So before I came here, I was debating in terms of what topic I will talk about, and I can talk about a more traditional topic on traffic signal optimization and related with the business I built at DD. And another side of my research related with testing and evaluation of autonomous vehicles, and this is really, I would say, a timely topic. However, it's not really being discussed in the transportation engineering field. And so since we have lots of students and faculty over here, I decided to talk about this just to explore what the new topics can be for transportation engineering as a student in transportation engineering as well. So I'm going to talk about the topic. I'm going to talk about the scenario generation of testing and evaluation of automated vehicles. And I'm going to start with how to test a vehicle. We are transportation engineers. We don't really do much of these. We don't really concern much about these. And usually to test a vehicle, whether it's a car or truck, there's 3 different types of tests, and all of these are vehicle-centric. So we do crashworthiness test in terms of bumping the car, in terms of crash avoidance. We do emission tests related with pollutions and fuel consumptions. We do durability tests. The car is running, very long time within the test track and things like that. So these are the car-centric, really the test before the car can be put into the usage. At the same time, we also do driver tests, right? So before for drivers, you first test your vision. Essentially, that's your perception systems, and then you need to know you have a good vision. You can see the objects on the road. We do written tests so that you know the traffic rules. So you have enough knowledge in terms of to guide you through the traffic flow. And then the last one, you do have a load test, on-road test. So there's someone use a rubric that check on different things like parallel parking, turning, and things like that. So that's what we do in terms of the driving performance evaluation and test. Now, think about automated vehicles. Now, for automated vehicles, you don't have a driver over there, and now you want to put that automated vehicle into the traffic. Now, how are we going to do the test? So that brings the issue for automated driving system. The ADS is a combination of vehicle itself. There's still vehicle dynamics, vehicle characteristics associated with these car mechanical systems. On top of that, we have this automated driving systems, essentially replacing a driver and taking a driver out of the loop. Now, when we talk about traffic flow, we talk about individual drivers really is the one who is responsible for their own safety, mobility and things like that. But you don't have it anymore. You have this automated driving system drive in the traffic flow, whether this is all autonomous vehicles, or sometimes it could be particularly during the transition time, it could be a mixture of the traffic flows. So in terms of the test, not only we still need to do the safety, the emission, the durability test of the mechanical system, now we need to test this automated driving system. And how are we going to do that? Are we going to do the vision test, do the written rules, the written test, the on-road test, and how are we going to do that? So the key of that is you need to put these automated vehicles, the automated driving systems, into a traffic context. So it's not just the vehicle itself. Now, because we're going to utilize this vehicle in a traffic flow, so you need to test these vehicles in a traffic context. So this is very, very different with traditional vehicle test, the test I was talking about. So if you look into this, and when you put vehicles into the traffic flow, now who study traffic flow? We as a transportation scientists, we study traffic flow. We know how traffic flow works. So this is actually the testing and evaluation of automated driving system is also a transportation engineering problem. So I started this problem about 5-6 years ago when I joined University of Michigan, and then I was one of the designers for the testing facility at the University of Michigan, and then start to learn how we're going to do the test for autonomous vehicles. And then really find this is essentially a transportation engineering problem. And then there's a lot of knowledge you learn from your traffic flow theories can be applied into the testing and evaluation of the autonomous vehicles. And I will show you of that. So obviously, testing and evaluation of autonomous vehicle is important. Everybody concerned about safety, mobility of the autonomous vehicles. There's just, at least I put down two probably most notable fatality, fatal accident related with sort of autonomous vehicles. You can argue in terms of the layer levels, but they are essentially being utilized as autonomous vehicles. One by Tesla in 2016, one in 2018 by Uber. They are highly automated driving systems. So obviously, safety, functionality, mobility of test of these ADS is very important. And how we do the test, how we assess these autonomous vehicles. Traditionally, I would say we have 3 established methods to test these ADS. And by simulation, obviously, by simulation. So essentially, You have a simulation model, you put your ADS into the simulation model, and this ADS will maneuver through this traffic flow, and you do it multiple times. It's quite efficient in terms of how long you can drive. In a simulation, you can drive very long mileage. Waymo has logged billions of miles within simulation. But there's a problem with this simulation model that it may not be realistic. So this is a simulated world. And the other extreme is on-road test. So you can put these autonomous vehicles on the road and then just driving through, let these ADS drive through the traffic flow. That's what people are doing for these AV developers, such as Waymo and Uber and alike. They have developed these ADS and put it into onto the public road to do the test. And for this type of testing is actually quite inefficient. So even for Waymo, they have such a large fleet, they probably can only do not many miles. And so far as I know, they probably have 10 million miles or something like that with their very large fleet. And in the middle somewhere was this test facility. This is a closed test facility. And so you have an urban environment, and you can test these autonomous vehicles through this urban environment, but it's simulated. It's not a real city, but it's a closed test track. And so it's semi-realistic. It's not entirely, but comparative to the on-road test, it could be safe, because on-road test, as I mentioned, that could be accident and could create a public hazard. And this in terms of efficiency is somewhere in the middle as well. You can also log a lot of miles because there's a lot of, you can run and get a lot of miles. And it's at the same time, you can create scenarios, right? You can test these through traffic scenarios, and then you can repeat these tests. It's more important to say this is a repeatable test. On-road test, a lot of time is not repeatable. Simulation and closed test track, these are repeatable tests. So I'm going to mostly focus my talk. It's mostly going to focus on how we do the scenario generation for test facility. However, this type of methodology can be applied directly into simulation models. And so essentially the first two topics. I'm actually having a project right now looking at the on-road test, which we're going to talk about at the end. So this, for testing facility, let's come to our M-City test facility. This is a small miniature city, has 32 acres of land, just right beside University of Michigan Transportation Research Institute. And it was built in 2013 and 14. And I was one of the principal designers for the M-City. I designed basically the control systems for it. And then you can see on the right-hand side, that's, give you an urban view. However, these are facade. These are not real buildings, but create a city scene. There are two major limitations for this test facility. You can tell that for a test facility, these are empty facility. There's no background traffic. And just to create that background traffic, if we bring real traffic into it, obviously it's costly, it's a hassle, but there's no background traffic into this. But they give you the infrastructure. Also, there's no testing scenarios. So because there's no background traffic, so the autonomous vehicle can interact with the infrastructure. However, there's no other road users within the test facility. So these are the two major limitations for this type of testing facility. So what we do, one of my research projects in the last 3-4 years ago is to create these what we call augmented reality testing facility. What we mean is, in addition to the physical facility, the testing facility itself, at the same time when we do the test, we create a simulation model for it. The simulation model provides all these virtual vehicles. These are simulated vehicles. And each of these simulated vehicles, we utilize their location, speed, heading, and things like that, those information. We code it into basic safety message for connected vehicle. And then we send these messages, these are simulated vehicle messages, and send it to M-City, the real facility, and send it to the real physical roadside unit. The roadside unit will broadcast these messages in turn hertz. So every 0.1 second, they broadcast these messages. And so for these test vehicle, they will be able to receive these simulated vehicle information. Although they're driving in an empty facility, but they receive all those information through the roadside unit. And so we can create these testing scenarios, because then we can manipulate all these simulated vehicle in terms of their location, position, speed, and things like acceleration and things like that. And at the same time, these real vehicles testing in the facility, they also control one of the vehicle within simulation model. So within the simulation model, these testing ADS also control one of the simulated vehicles, and so they can interact with other vehicles in the simulation. So I want to show you a video. So this is this is a video that show you essentially what we did. This is on the left-hand side, this is a simulation model. And on the right-hand side, that's physical M-City testing facility. On the top of that corner, that's the physical real testing vehicle. This is a level 4 ADS, autonomous driving system. And so driving in the real facility. And on the right corner, that's the HMI within the autonomous vehicle. And essentially, these are the user interface for the safety drivers. So that car, you see the yellow car, these are essentially this real car. The control one of the simulated cars. This car actually interact with other simulated vehicles. This real car will need to react to things like that. So this is one of the scenario we do the test. This is a real test to test this. To actually test the functionality of let me just for their reaction to the red light running. So we need to tune up the parameter for the red light running to see whether this vehicle will be able to really respond to those vehicles that actually break the red light. So you can see that's our vehicle. This is one of the scenarios I just showed, which you can see that actually you can see this vehicle actually stop over here, waiting other vehicles to pass by. This is a real vehicle, although you can see there's nothing over there, but they receive the information. And so now the next one is to look at a red light running scenario. So this is the vehicle, and this is red light. There's a simulated vehicle, break the red light, and then we want to see whether this vehicle will be able to react to it safely. And then there's a set of parameters to adjust the control algorithms for the autonomous vehicle, and then we utilize this to repeat the test to adjust, to optimize these parameters. And as I mentioned, the simulation model we utilized in this context is VSIM, so you probably know VSIM really well. And the real vehicle we utilized, this is Lincoln, and this is being installed all sorts of sensors, LiDAR, radar, and cameras by autonomous stuff. And so there's also a by-wire data collection system inside of it. Okay, so within the simulation, you can create all sorts of scenarios. This, for example, we actually create a train, a simulated train, and we actually, in the facility, there is a railroad crossing, and then this vehicle actually need to wait until the train passes by, and that vehicle will be able to move. And if you want to see those, this is actually on the YouTube also, so you can find it on the YouTube. Oh, so that's one. The second thing we need to do is to create these testing scenarios. So this can be utilized not only for testing facility, but also for simulation. So testing scenarios. Now, if you look into on-road test or look into how we test these, if you want to enumerate the scenarios, it's impossible. There's so many scenarios. And even to create a fatality, and by human driving performance, 100 million miles, we have one fatality. So even with so many dollars into the ADS development, we even don't come any close to these miles. So we need to be able to accelerate this type of testing by creating significant or critical scenarios. So if you want to test all sorts of scenarios, there's a few things you need to consider. One is these behavior competencies in terms of driving. There's whether they will be able to cross the intersection, whether they will be able to stop at the stop sign, and things like that. And you need to be able, so there's a list of behavior competency you have to test. There's a list of different situations. There's sunshine, there's raining, and there's different geometry, different road. And then there's also different scenarios. So even in the same scenario, let's say the cut-in scenario, the vehicle cutting in front of you, there's different cut-ins. There's the range and the range rate between the host vehicle and background vehicle can vary very much. So all of these need to be considered. So if you want to enumerate that, this is just the mileage to do the test. It's just so much. So what we do is we need to generate what we call critical scenarios. So if I utilize this to represent the scenario space, all sorts of scenarios we need to cover. So what we want to do is we only test a small number of scenarios, but these scenarios have significance. And so these are what we call critical scenarios. So in order to do that, the first thing we need to do is to define what is critical. What is the criticality? So criticality, by definition in our contents, what we propose is to look at two things. One is maneuver challenge. What we mean is this is a challenge to the ADS. If it's not a challenge, then this is probably not so much useful to do the test. For example, if we do the car following, testing the car following performance, if the car really far away from you, this type of car following is not very challenging. It's not very useful to do the test. So you want to test the level of the challenge. The other thing is what we call exposure frequency. What that means is that if the scenario will have very, very low chance to occur in reality, the importance to test this scenario is also small. So we want to test both challenging but also frequent scenarios. So this is a combination of maneuver challenge and exposure frequency. So theta over here, the theta over here represent environmental type of parameters such as sunshine, traffic conditions and things like that. And x is the decision variable. These are the control variables for surrounding vehicles for the scenarios. And s over here in order to evaluate the maneuver challenge, if we don't know how ADS, exactly a specific ADS, how it works, we need to utilize a surrogate model to test maneuver challenge. So the surrogate model we create, essentially it's just trying to capture a common features for these ADS, which is, I think it's common sense. So even for ADS, they need to be able to follow other cars, they need to be able to do lane change and things like that. And we want to capture that through a surrogate model, even we don't exactly know what the ADS model we're testing. Okay, so now come to how we do generate these testing scenarios. Now we define the criticality measures for testing scenarios. For any testing scenario, we can calculate the criticality. And now we need to find a small set of scenarios which can help us to evaluate the performance of this ADS. But when we evaluate these ADS, for example, if we care about their safety performance, we care about the accident rate, then the accident in the real world is actually very small. These are rare events. So if we put the test, the on-road test, put the vehicle on the road, then the mileage is very, very high. And this is what we're doing for some of the testing. This is essentially for public road test. Given all these background environment, you need to test out all the situations and then to look at the accident rate. And this is essentially what is the probability of given certain scenarios, what accident, the probability that accident will occur. Okay, so obviously this is, if we want to do that, we want to discretize that, we can put the vehicle onto the road, sampling all the scenarios, and then calculate over the scenario, scenario space, how many accident occurs, and divided by the total, sampling size, then that gives us in terms of the estimation of that. That's how we do the on-road test. Now we want to accelerate that. So the way to accelerate this is through the importance sampling theory. So what we do is instead of sample from this on-road type of test, what we do is we sample from this Q function. So you can see we multiply, and also on the numerator and denominator, we both have a QX over there. This is an important function. And instead of sampling from this, we sample from this QX. And then because QX is a selective portion of this, so the sampling of that, and then as long as I can guarantee my confidence interval, then I should be able to recover in terms of the performance of this vehicle's safety. So now we come to this is established theory in terms of the QX, in terms of the importance sampling. This has been known for a long time, and in this context, let's just define this as what we do for to select a set of critical scenarios. Now there's two problems. One is we want to make sure when we sample from this importance function, this is accurate, meaning they can really reflect in terms of the accident rate if comparatively to the on-road test. The second thing is that the required test, the number of tests we do, is significantly smaller. We don't want to do the big space, so we need to be efficient. And so what we have developed is to look into how we do that, and by looking at this different type of test. So how we do, first of all, we need to look into, if we create this critical scenario, what will be our sampling method? So we can do the greedy sampling, meaning that according to which scenario has a higher critical value, then have a higher probability to be sampled. We can do epsilon greedy, is essentially balanced exploration as well as in terms of the importance of the scenario. And then we can theoretically, we can actually prove that if we apply this, if we have a scenario covers all the critical scenarios, then obviously, then this is unbiased estimator. And this can be proved, and basically to say, if we apply the epsilon greedy sampling methodology, we can balance the exploration and the exploration, and then to guarantee this estimator is an unbiased estimator.
Do you have a degenerate problem in sampling process?
What do you mean degenerate?
Because I can ask later.
Yeah, go ahead. Yeah, no, go ahead.
Because you sample repeatedly, right?
Yeah.
And you sample based on your importance criteria.
Exactly.
So over time, those with low importance criteria scores will be out. And so your sample will be smaller and smaller. So that's what typically happens. It's what we call a degenerate problem.
In this particular problem, it usually is not so much because the scenario space is so big. It's very, very big. So taking out one of the scenarios, you will see, taking out a few of these scenarios is actually not so much a problem.
But I suppose your sample scenarios with importance scores is a small subset.
Yeah, even that small subset is still quite big.
Oh.
Yeah,
Okay.
still quite big.
Okay.
The other thing is efficiency. And with this greedy sampling policy, we can guarantee that it's actually a small subset of this and can actually recover the relative half bandwidth to ensure the confidence interval. So one of the things will screw up, will enlarge our sample size is what we call the dissimilarity. Because before we do the ADS testing, we don't exactly know that ADS model. We are third party to an ADS. So we don't know how that specific ADS works. So to generate a scenario, we actually start with a surrogate model we just mentioned. And so the surrogate model and the ADS actually have a difference. And the difference actually will essentially enlarge this variance. When they enlarge the variance, then essentially we'll have to make more samples out of it. And so, so if we know exactly that ADS, then we know the model, then the sampling size will be even smaller. So then with this sampling technique, and we can develop this type of framework, one is we need to generate this library of scenarios. And I'm going to show you some of the examples. Once we generate this library of scenario, we sample from this critical scenario set, and then perform the test either in the simulation or in the testing facility. That's what we do. Okay? I'll give you 2 case studies. And one of the case study is a simpler case, lower dimension case. This is a cut-in. You have an ADS, you have a vehicle cut-in, and you want to see this ADS performance. So this is a lower dimension. I will show you why it's lower dimension. The other one is the car following. So if I follow the car for a certain period of time, and then you can actually, for each time instant, you can control the range and the range rate and speed of that background vehicle. This becomes a very high dimension. So we want to show you how we do this by applying this framework. And the data we utilize is 2 databases. One of the advantages at University of Michigan is that because we're in the backyard of our automotive industry, so we work a lot with these OEMs. And so there's 2 big databases within our Transportation Research Institute. One is what we call Safety Pilot. This is one of the largest connected vehicle testbed in the city of Ann Arbor. And some of these vehicles not only installed, equipped with the onboard unit, and they can communicate with the roadside, but they also have inside of the vehicle, they also have mobile eye, they have radar, they have LiDAR system with it, so they can collect data from the surrounding traffic as well. So about 140 of these vehicles actually equipped with mobile eye and our data acquisition system. And there's another database, what we call the IVBSS. This is in the 1990s, there's a group of vehicles being tested, and some of the vehicles have this radar and also LiDAR system being installed, so we can actually know in terms of the surrounding traffic as well. So we have both these databases can be utilized to help us to understand, to generate these exposure frequencies in terms of these scenarios. Okay, so this is the cut-in scenario. So cut-in scenario, in order to do this, and the reason we make it low dimension is we only control the range and the range rate. So at the moment of cut-in, in terms of the background vehicle, what is the range between the Eagle vehicle and then the range rate, the speed difference of that. So these are the only 2 parameters we're controlling. These are 2 decision variables. And then now we need to search all of this big space. We need to search these critical scenarios. A lot of these scenarios, the criticality is 0 because they are very safe. So these are not very important to us. So what we want to do is we want to search those scenarios which higher criticality. And because the space is big, and then we don't know where we will have these critical scenarios, so we want to develop these auxiliary objective functions to guide us to select those points, those scenarios, which has a higher criticality value. And then the way we do it is to consider both, obviously, maneuver challenge as well as the frequency. The maneuver challenge in this case, because of this just a simple cut in, we're looking at time to collision. Okay, and this is a little bit, I would say, modified time to collision measure because when it's negative, it's become useless. So we make it positive. It's enhanced because we can consider over the process the acceleration rate. And also, in terms of how we know in terms of this scenario frequency, what we look at is we'll create a high frequency region, which is this omega. And then we look at the scenario distance to this region. And so there's a distance measurement in terms of how we look at whether this scenario will be a highly frequent scenario. And now, if we have both of these, we calculate for each scenarios, we calculate their criticality. We choose those scenarios which has a higher criticality measure, and then we have a set of critical scenarios. We sample all of that, and then we put it into the test. And so what we utilize is the safety pilot database. And the safety pilot database is running starting from 2012, and up to now it has been 8 years. So we get lots of data. And we query one scenario, which is this sort of cut-in lane change scenario. And we utilize about 400,000 of these data. We look at in terms of during these cut-in, what will be the range and range rate distribution. And here shows you in terms of the distribution of these. And obviously, in a lot of the cases, is somewhere around 0, which is the speed difference is very small. The range could be, very different. So this is a highly frequent scenarios. And for all other scenarios, we look at the distance between this specific scenario to this omega zone. And that's gives us in terms of the frequency measures. And then for the surrogate model, we utilize this Gibbs model. There's a car-following model we all learned, the GM model, the Gibbs model. There's a lot of car-following models we have discussed in the traffic flow theory, and we use a Gibbs model for this case. And then, so this is the exposure frequency. And then by utilizing the Gibbs model, we can evaluate it in terms of the safety performance by simply looking at whether there will be accident created. So you can see that this for the same parameter, we can calculate whether this is safe or not safe. So not safe meaning there's an accident occurs. And if you take a product of these, then that gives us the criticality measure, and this has become a small set of scenarios we sample all of that. And then we do the test. For this particular test, we actually tested in M-City facility, and we use a real vehicle. And this is the testing facility. This is augmented reality we have been talking about. This is our library generation. So we generate this scenario, we sample from the library, we put it into a simulation model so that we can generate background vehicles, and then we put it into the test. And this is actually a execution in terms of this field test. So this is a cut-in scenario. And again, this is simulated M-City. This is the driver's HMI. And if you can see, this is the host vehicle. And there's a simulated vehicle cut in. And then the parameters governed by the testing scenario library. So we sample from library, and we put it into the simulation, and then to do the test. And the first test, you just see, and there's no crash at all. And because you can see the range and the range rate, there's a range over there. And for this particular case, is almost a crash, a near-miss situation, because the distance between these two, the range become very, very small. So the third scenario is there's a crash, and you can actually see from there, or you can see from here. This is the following vehicle. This is the the vehicle in front, and that the distance between the two become negative, meaning they bumped each other already. Okay? So this is how we did the cut in the low-dimensional scenario test. And if you put it into figure, and then you look into the whole scenario space, and you compare with the number of scenarios we can choose from the critical scenario library to obtain the same half bandwidth, we can actually accelerate this about 10,000 times. So it's quite amazing in terms of how much you can accelerate this test to obtain the same performance. The next one is a little more complicated. This is the car following case. The reason the car following case is actually seemingly very easy, but if we want to have a scenario for a long period of time, let's say 30 seconds, every second or every half of the second, I need to control that, the range and the range rate between these two vehicles, then the dimension is very high. And with that high dimension, as I mentioned, a lot of these scenarios are very safe scenarios, 0. So I need to be able to find those has higher criticality values scenario. So to do that, what we do is we develop this MDP process, the Markovan decision process. And for this, the state defined here is the background vehicle speed, the front vehicle speed, the range and the range rate. That's the state in terms of the car following. The action, which is the acceleration rate in terms of that background vehicle. So the acceleration rate, meaning they could decelerate, they could accelerate. And now we define a state action pair by looking into both this exposure frequency as well as the maneuver challenge. By exposure frequency, what I mean is this is the state. And at this state, what action, the frequency of that action, the probability of that action. And this is given that state, given that action, what the probability of the accident will occur. So again, if it's longer range, even the taking action, the probability of accident occur is very small. Those are not very critical scenarios for us, or not challenging scenarios. And I use S over here because I use a surrogate model. If it's A, meaning this is on-road test, or simulated on-road test. So I create this pair, and then now you have a sort of a decision tree. And then for each of the scenario, you essentially from the root to a leaf by doing this state action pair. And so the probability will add up all together for that specific scenario, the criticality measure. And we can actually prove that if we do so, then essentially this recovers what we have defined in terms of the criticality measure. And so to learn, because again, the scenario space is so big, a lot of these scenarios are just 0. So we need to find these critical scenarios. So what we do is we utilize reinforcement learning to learn what are the critical scenarios. So if an accident occurs, we get 1. That's the reward. If no accident occurs, we get 0, which is the reward measures. So we run it multiple times and to train the model and to remember or to memorize what are the scenarios which might generate higher critical values. Okay? And so this is what we do when we compare in terms of a very large space. Now we have this generated critical scenario space, which is being generated by this reinforcement learning model. Now we can compare in terms of the difference. And we actually utilize one of the scenarios, one of the ADS models, which is utilized by my colleague Hui Peng's group's work, utilizing adaptive cruise controls model, and plus their the AEB, which is the automatic emergency braking model to control that background vehicle and to compare if we generate scenarios from the on-road test, then with this critical scenario library we generated, sampling from both these and compare their performance, and you can actually see the half bandwidth which gave us in terms of the confidence levels for this NDD. This is naturalistic driving situations, and you need to run like 1.5 times by 10 to the power of 7 times. But if you look into utilize the generated library, or with the technique we just discussed, this is less than 100 times. So the acceleration of this testing is very, very significant. Okay? So that's sort of the work we have been doing in the last few years. And the first paper, this work has been going on for 5 years or so, and we haven't published any of those. And the first paper just came out this month at the IEEE transaction. And there's a part 1 paper, there's a part 2 paper, and the part 1 paper talking about the methodology we have developed, and then part 2 papers discuss a few case studies, which include one of those, include the cut-in, the car following scenarios and things like that. And there's a number of projects we're also working on in this space. One is to look into how we can enhance the augmented reality. The augmented reality right now is simulated vehicles and these vehicle messages being broadcast within the MCD, but we can only test the planning algorithm. We can't really test the perception. Remember, for ADS, there are three critical components. One is perception, one is planning, one is control. For the current augmented reality can only test planning. We can't really test perception, meaning we don't see how well this car can can sense the surrounding world. And to resolve this issue, we need to add sensor simulation to it. So we're adding sensor simulation into this augmented reality testing environment, and to create an integrated driving simulator. For testing scenario library, we have 3 ongoing projects. One is looking at extremely high scenarios. We talk about car following sort of a high dimensional scenario, but if you put into the context of either highway or city testing, so if you looking at a city, simulate a city, and then you test this ADS, then the scenario space is much, much higher than that. And so with that, how we do the testing of that. And secondly, we know that there's dissimilarity between the ADS and also the surrogate model. So once we test your vehicle, after a while we know better in terms of your vehicle performance, we can actually generate scenarios according to our previous test. So there's also adaptive testing. Also, when I test your vehicle, I know your performance. I know how we can train you better. So testing and training of the ADS is the 2 sides of one coin. So this is important not only for just testing of these ADS, it's also important for development of these autonomous vehicles. So testing of these training of these ADS is also being part of our work. Now, there's also other things we're doing related to this space, how we assess the safety. Intel has, Mobileye has this RSS model. There's a bunch of other models has been proposed. And then one of the NISA project we're working on is to evaluate all of these notable safety assessment models. And hopefully we can also propose some new safety assessment models. The other thing we look at is to help NISA to develop this driving performance test. So now it's not a real driver, but it's ADS. And so they want to develop a minimum testing procedure for the ADS and through the on-road test. So we're developing this on-road testing procedure by looking into some of the minimum criteria these ADS has to satisfy so that they can put on the real road. So as I mentioned, there's a paper just come out this month, and then the second paper will come out very soon. And there's a bunch of other papers will come out in the space recently. And if you want to check into the details of these papers, you can actually check on my group's website. And this website contains all of these papers, including some of the papers not being published. I've been working with, I have to do some acknowledgement, I've been working with a group of brilliant graduate students and postdocs and also research faculty. And most of these work is their work, and I have just to have the luxury to present here. And I also want to acknowledge my sponsors, NISA, and my center, my University Transportation Center, MCD, and also my previous collaborators or employers, which did give us some funding in terms of this work as well. So I have to acknowledge my research sponsors. At the end, I want to show you my contact information. If you have questions, you can ask now or you can ask me later on. Thank you very much. Yeah, go ahead. Go ahead. Yeah, go.
So your scenario generation, I suppose one of the purposes is to identify corner cases that are rare events, right? And so I guess my question is, I just want to hear from you, how confident are you in terms of identifying corner cases that haven't happened in reality?
I first want to differentiate. We're not really interested in corner cases. We're actually interested in edge cases.
Okay.
So there's a
you should define.
You have there's a differentiation of corner cases versus edge cases.
Okay, so please.
Okay. So edge cases are these. So think about a linear program, and then that's your feasible region. Your solution is actually at one of the corners. The probability of that corner cases occur very, very small.
Right.
However, the boundary of that's where we are interested in. So the boundary of that's the edge cases. Okay? So we're interested in edge cases, not exactly corner cases. And so to identify these edge cases, we'll give you two criteria. One is the occurrence frequency. One is how challenging it is. When it's become challenging, you're pushing to the edge, right? If it's not challenging, it's somewhere in the middle. So it's safe scenarios. Because it's challenging, so it's into the unsafe situation. But at the same time, we want to make sure this is a case can exist in the real world. Okay?
Can I ask a follow-up question? So why are you not interested in corner cases? Or maybe, for this project, so is that because you think it's less important, or it's
No.
harder to capture, or maybe tell us some of your
Okay.
opinions. Thank you. I'm done.
Corner cases is one specification of edge cases. So we're not really interested in just a special cases, because that special cases may not exist, may not occur anymore in the real world. So it's not really interesting to us. But we're interested in the whole boundary of that. It might include that.
Okay, so
Corner
then answer
case.
my question now.
Well, I thought I answered your question.
No?
Jeff?
Yeah, go ahead. Yeah.
It's kind of follow-up, but when you generate my understanding is you sample from the data, right, the real data. But the real data is from human-driven vehicles.
Yeah.
So I see this is kind of like a gradual process to reach the final autonomous driving, because this is not autonomous driving. So many of the issues from autonomous driving cannot be reflected from the data. You're basically simulating autonomous driving, then there's a human-driven vehicle try to cut in. That scenario can be probably better captured versus there are two autonomous vehicles. Maybe there's some problems with the perception systems, right? That scenario cannot be generated.
Yeah, again, that's
sampled.
we're not really looking into the perception systems.
Right.
And then, but to do the test, we can. One of the things we were thinking to simulate some cases with the performance of the perception system is sometimes we can stop sending these basic safety message. Let's say, in some cases we just stop sending these message so that you don't receive this information, mimic that your perception system actually did not sense the object on the road. So that could be, we haven't really done anything like that, but that's one of the remedy we can actually utilize. But again, this sensing system really need a sensor simulation incorporated into it. Wow.
Oh, not as soft a catch as Jeff.
Yeah, wow.
So it seems, presumably the goal here is to improve safety, improve the responses of vehicles to these different conditions that they encounter. And so it seems like somewhere in here both the probability and the severity of these different situations evolves, because the vehicles become reprogrammed, so the consequences become less severe and the probability of being in that situation changes. So is there some way in here that you capture that kind of feedback loop, and over time things that used to be higher probability and more severe now become lower priority and less severe, and new things rise to the top, and you work down the edge towards the corner a bit?
My short answer is I don't know. We thought about that. There's a lot of these OTA, over-the-air update. Once autonomous vehicle, the ADS being updated, how do you certify that? It's just, you did your testing for the current ADS, but once they do the update, how do you do that? This is still a problem we are thinking how to solve it. And actually that's one of the things we're looking into on our current NHTSA on-road project. So NHTSA can say, this is, you allowed to do the test, or you allowed to put your vehicle onto the road. But if you update it, should we give you the permit again? So that's something we're looking into, or we don't really know yet. The current one we consider, the current evaluation loop, we don't have anything like that. We're being given, let's say, this is the current ADS, we're going to test your current ADS. The update of that software is not being considered.
You just need to update the data and test.
So you might need to test again, but...
And also the data, not only the testing, but the data
The-
needs to be updated.
Yeah.
Any other questions?
So I have two questions around your work of the scenario generation. So you tested these scenarios on a vehicle as augmented reality, but is there a step before it where it's always done in simulation, so where vehicles are tested in simulation? And if so, what tools are used, like hardware and software? And the other question is, do you consider future scenarios, like when we'll have more vehicles or something like that? And if so, how do you generate the population of vehicles in future?
You mean the future AVs?
Or just future road vehicles in general, like the fleet in future, let's say.
So we didn't do any work on that simulation model. We just used a commercial simulation model, which is very popular in the transportation field, which is Vision. So all the background vehicles are controlled by Vision. Okay, I shouldn't say all the background vehicles. For the testing background vehicle, it's actually controlled by our scenario generation. But all the rest of it is controlled by WISM. So all the behavior rules of WISM will apply. So we didn't do anything in terms of the simulation model itself. How do you generate the future scenarios or things like that? And one of the current projects we are working on is actually utilize a calibrated simulation model. Let's say I can create city of Ann Arbor traffic simulation. Then I can put my ADS into it, maneuver through this from given origin destination, maneuver through it. And we can actually reproduce the test you're going to do on road. So given origin and given destination. But the scenario generation become a lot more complex in that case because you're not only just following, you also have a lot of other situations. So scenario generation become a real issue for us. And our current thinking of that is it's not just limited to reinforcement learning. We have to use deep reinforcement learning to learn all these scenarios.
So Henry, that's a very interesting presentation. I also have a question.
Sure. Go ahead.
It looks like there are several challenges for the autonomous vehicle, but what you are creating the critical scenarios for accelerated testing is for those CAVs, right?
Yeah.
Because you rely on the information through the roadside unit, go to the tested advanced vehicle. But in the reality, if you have an autonomous vehicle driving, you rely on the sensor's response to the changing roadway environment. In your case, you rely on the roadside unit to pass the information to the vehicles being tested. There's going to be a kind of a delay through the communication, even that's small. But there is also the sensor latency for perceiving the change of the condition. So I think maybe this is a good accelerated testing for the algorithms, but there's nothing to do with the sensors that equipped with the advanced vehicle. Is that correct?
It's nothing related with sensor. However, I should say, in the AV development world, if an object is being detected with a latency of outside of 200 milliseconds, it usually become useless. So 0.2 second is a threshold utilized by many developers. And our whole flow coming from simulation and package it, send it to RSU, broadcast received by OBU, and the whole process over will be within, most of the cases will be within 200 seconds. So that information can be still utilized.
Yeah, so I think the time should be reasonably short.
Yeah.
Another thing maybe is also my recommendation to consider is if you learn from the simulated scenario, that's still different from the real world scenario. So how confident we are using the simulated scenario to train the autonomous vehicles?
That's a very good question, and we are still thinking about it. When we say accelerated training, then one of the things we will need to argue is that when we utilize these simulated scenarios to train it, is this really can be applied to the real world? So that's one of the things we are working on. And what I want to say though is when we say accelerated training to generate these testing scenarios, a lot of these is sampled from the real cases. So we need to have a large database to generate these so-called exposure frequency. That's where the data collection becomes very, very important. So one of the projects we're working with Didi is to look into, they have video cameras in many of their cars. So they can create a lot of these scenarios through the real world. And through that, we can generate exposure frequency and then help us to identify the critical scenarios to whether it's through testing and whether ought to do the training. So that's a real question need to be answered.
I think that's great. No matter what, I think this is a very useful research for both the researchers and the industry. I know we are running out of time. If there's a last question, maybe we can give the chance. Otherwise, I think Henry is going to stay at the reception. You guys can keep talking to him. Thank you very much, Henry.
Thank you.
So that was
It's
a great
a pleasure.
talk. Thank you.